Okay, we have here today a really interesting problem from the SwinBee 2018. This was problem 16. We have the integral from 0 to 2018, absolute value sine 2018 pi x dx. Okay, now before we get to dealing with this absolute value, I think the thing that bothers me more right now is what we have here on the x. I really want to simplify that, and I'm going to do that with the u substitution. So I'm just going to call this whole thing my u just to deal with this. So we'll say u is 2018 pi x. We'll take a derivative. Du is just going to be 2018 pi dx. And I think what I'm going to do is just solve for dx. So we'll write dx in terms of du. We'll write this as by dividing by 2018 pi on both sides. We'll have du over 2018 pi. Then we'll go ahead with the substitution. Now, first we'll take our upper bound. We'll plug this in here for x. So plugging in 2018 here. Now our upper bound kind of becomes worse because now our upper bound is 2018 squared times pi. We'll plug 0 in here, and that just gives us 0, so that's okay. Then inside the integral, this now becomes just sine of u, or absolute value sine of u, and our dx is going to be du over this. But I'm going to take, this is a constant value, so I'm going to take this out front of the integral, and we'll write this as 1 over 2018 pi. But now at this point, this would be a really easy integral. We know how to deal with sine, but what about absolute value of sine? Well, I think what we could do before we integrate this, let's just take a look at a graph. Okay, now just looking at this rough sketch of our sine curve, and this is without the absolute value, we're just looking at sine of u. I'm not interested in the negative values because our bounds are starting at 0. I only drew this to about 4 pi, but the thing to notice is this, of course, goes on forever. But now this curve just repeats itself, so like the area here in this first area from 0 to pi, that's going to be exactly the same as this area from 2 pi to 3 pi. And the same thing here. This is going to be the same area as this one, just negative. But now what's going to happen when we apply absolute value on this? If we apply our absolute value, all these negative areas are just going to become positive. So like we could redraw this kind of like this, and we could redraw this one like that's terrible, but okay, that's kind of like that. So applying the absolute value on this, now we just have no negative values, nothing underneath the x-axis here. And so now for every pi, we really have the same thing from 0 to pi. This area is going to be the same as this area. This is going to be the same as this area, which is going to be the same as this area. So when we integrate, all we really need to worry about is integrating from 0 to pi. And then we're just going to need to multiply that integral by however many of these curves there are. And we actually know it's going to be 2018 squared because we're breaking this up on every pi. Eventually out here, we're at the point 2018 squared. So it turns out we just need to integrate this from 0 to pi, but we just need to do it 2018 squared times. Okay, so now based on what we found from the graph, now I've rewritten this just integrating from 0 to pi and just multiplying it by this 2018 squared we have here. But when I do that, first we can have some cancellation because we have 2018 squared over 2018. So I can cancel this with one of these. So out front of the integral, we're going to just have 2018 over pi. Then integrating this is just going to be minus cosine of u, and we just need to evaluate this from 0 to pi. So now we'll plug in pi. We have our minus out front. Cosine of pi is going to be minus 1. Minus, then we're going to have, again, a minus out front. Cosine at 0 is just 1. Minus times minus here is a plus. Minus times minus here is a plus. So this whole thing is actually just 2. So just multiplying 2 times 2018, for our final solution, we'll have just 4,036 over pi. Okay, thought it was a really good problem from the SwinBee 2018. If you're interested, I can provide a link in the description to their website. And if you're not familiar with this contest, it's from Swinburne University of Technology in Australia. So we'll stop it there. Thanks everyone for watching. Have a good day.